So today, we're mostly going to be talking about conservation of energy. But before I do, I want to speak to this kid on a swing problem. So we'll just reduce the kid to just a box, and the swing will have a light rope of some sort. And put two of them here because the idea is the kid's parent or friend or, I don't know, sister, brother, pulls them backwards and then releases them. And you're asked several questions about what happens because of that. To do the work to actually figure this out, there's an intermediate part, a part in the middle where the kid is being pulled backwards. So let's consider that for just a moment. Let's assume that we're still applying a force like this to pull the kid backwards. You had a test question like this once, where you had to figure out, the force required to pull them backwards and show that it had something to do with the angle. If you work that problem out, just trying to figure out how much force is required to pull them backwards, it should be clear that the force becomes greater the more you pull them backwards. That's what you should have figured out. There's just three forces here. So you're resolving weight, tension, and the applied force. And so clearly the applied force is not very much at the very beginning, but as you pull them backwards, you're doing more to lift them than you were before. So if you worked it out, you find that it has to do with the tangent of the angle. And that kind of gets you an idea for how much force you're applying. But the issue is, if you wanted to calculate the work done in moving the child from here to here, you could do it by using the work expression, but this expression won't cut it. And the reason is because, think for just a moment, delta x represents the direction the kid moves. That's going to be in this direction. So the angle between the applied force and delta x is here, and it's always changing. It starts at 0, but the moment you start pulling them backwards, that angle changes. So this is changing the entire time you are applying the force. In addition to that, the force is increasing the entire time you're applying the force, which means you can't use this to figure out the work done. Instead, you'd have to use this, where ds represents the curve length that you are moving along. And it's a dot product, so you would have to be dealing with the fact that the angle and the force are changing at the same time. That's a challenging question. You guys who are in calculus, you should do it, because it's not an impossible question. So you guys are starting to learn how to do calculus-style problems. The hard part here isn't actually in doing the integration. The integration ends up being really straightforward. The hard part here is in the fact that you have to set up this integral. You have to come up with an expression for the force in terms of ds or d theta or something like that. That part's the hard part. However, there's a much easier way to do this question, because ultimately, if you think through the problem just a little bit, you'll realize that the kid starts at one level down here and then is raised to a different level. So there is a change in height for the kid. That suggests that there's a change in potential energy for the kid, and that has to equal the work done, minus the work done by gravity. But whatever that work done by gravity is, there's an equal amount of work that you did in lifting the kid. Because the tension doesn't do work in this problem. And if you don't know why, you should be thoughtful about why the tension doesn't do work here. I will help you because you guys are not particularly good at this yet. But the tension is this direction, and the movement of the child is this direction. So the tension is always perpendicular to the displacement, which means the tension can't do work on the child. All the tension does is redirect the child. Everybody following? Good. Here's my issue to start this problem. In this kind of question, you're often given the angle and the length of the swing. Can you tell me what the height is in terms of the angle and the length? This is a geometry question. And this occurs so frequently in this class, I need you to be proficient at it. So take a second, see if you can figure out a triangle that might help you. My experience is that you guys struggle with this idea. But see if you can figure it out. I'll give you 60 seconds. Did you figure it out? Aw. So you guys didn't get L times 1 minus cosine theta? I guess I'll help you. I don't want to. I want you to figure it out. I want you to have the joy of figuring it out. But okay. How about I draw a triangle? A reasonable triangle. Is that a reasonable triangle? Would you agree that this is L? You guys agree with that? Okay. We know this is L over on this side. However, do you realize this is the adjacent side of a right triangle where this is the angle and this is the right angle? You guys see that? And would you also agree that this is the height? All good? So L equals A plus H. Is that okay? And how about cosine theta is A over L? Is that okay? So L equals L cosine theta plus H. That okay too? You see it all right? So H equals L minus L cosine theta. So H equals L times 1 minus cosine theta. Geometry. A little trig, but geometry. If you didn't know how to do that, you now know how to do it. Put a box around this. This comes up all the time. All the time. This is worth knowing. So you've got it? We're all good? All right. I'm about to erase it. I want to go back to the kid problem. There we go. Get all this out of the way. All right. Put this on the back burner for just a minute over there. I said something earlier at the beginning of this whole discussion, that work is the method by which you change something's energy. So if something already has energy, for example, if an object has, say, some potential energy and some kinetic energy, then your system has a certain amount of energy. Right? I'm just adding up all the forms of energy that you could have. But whatever the total energy of the system is, it's going to be the sums of all the different types of energy that there are. Through the course of our year, we're going to be adding to this list of possible energies. See, there's other kinds of energy out there that we haven't talked about. Our list will end at about 5 different types of energy. Translational kinetic energy, gravitational potential energy, elastic potential energy, thermal potential energy, and rotational kinetic energy. Those are all the energies that we have. But here's the distinction or the important detail. If we want to change that energy, you have to do work on your system. And that work has to come from an external force on the system. It can't be an internal force. So if you want to increase or decrease the amount of energy of your system, you have to do work on it. Now, to simplify this for just the next couple days, our systems are only going to have 2 kinds of energy. We're going to focus on just these 2. We're going to isolate our systems and make sure these are the only things that are working on our system. But what this also means, and this part's important, and I made kind of a mistake yesterday, and I want to rectify it, is that if you, technically what we're doing here is taking the derivative but I'm not going to use the derivative word. If your system is isolated and there's no work being done on it, then any change to the potential energy and any change to the kinetic energy has got to equal zero. Meaning inside the system, if there's no changes to the energy, if no work is done on the system, then the change in the energy is zero. That doesn't mean you can't have changes in the types of energy, meaning you can lose some potential energy and gain some kinetic energy and vice versa. But the change in energy has to equal zero if there's no external work being done on the system. This is for an isolated system. Now, if your system isn't isolated, which is quite reasonable, then the change in potential plus the change in kinetic would be equal to the work done by an external force. This is for a non-isolated system, meaning your system is experiencing an external force. It could be something simple like air resistance or friction. That's an external force. It would slowly bleed energy away from your system. But for friction to be acting on your system and causing work, the system has to be moving. But you can siphon off some energy, but you could also add energy to the system. Somebody could just push on your system, and that would give it more energy. Lift up the object or push on it or whatever. But these are the two ideas I wish to work from. You see, the idea here is that energy is conserved, which means that the total energy of your system stays the same unless you intentionally change it. Now, what this will result in is a means of solving problems where perhaps we don't know how the forces are acting in our system, or perhaps they're acting in a way that's complicated. Let's consider what happens here if you pull back on the child, bring them to some height, and then release them. Now, what I'm suggesting here is that this represents the initial state of the problem, and this represents the final state of the problem. That the parent pulled the child back. During that time, the parent was an external force on the system, and the parent added energy to the system. But the moment the parent released the child, the only two forces acting on the system was gravity and tension. Now, gravity is a conservative force. It's not an external force to the system. Remember, the Earth is part of your system. Tension is an external force. But as we showed a moment ago, the tension does no work because the tension is this direction, and the child's going to travel this direction. So although the tension is an external force, it's not an external force that does work. So before you start a problem like this, you should consider what the external forces are and ask if they possibly do work. Things like friction will do work. Air resistance will do work. But generally, a lot of your other forces end up not doing any work. The tension here does no work. It just redirects the child. With that knowledge, the change in potential energy plus the change in kinetic energy has to equal zero. Now consider what this will tell us. At the start of the problem, there is a certain amount of gravitational potential energy. I have lifted the child up above the baseline. Now, we talked about reference level yesterday, correct? We talked about baselines yesterday. A reference level and a baseline is something you can choose. I was talking about it when it came to like stuff on my desk, like does an object have potential energy? And we said, well, there's a lot of ways that you could interpret that. Now, if we're talking about the child here and the child's motion, well, I can decide what the reference level is. I can decide where we're taking a measurement from when it comes to how the object's potential energy is measured. In most cases, I think you'll almost always be better served to make whatever the lowest point the object can attain, make that your reference level. I mean, you don't have to. You can make any place you'd like the reference level. The child probably doesn't hit the ground. The child's probably above the ground. But we don't have to use strictly where the ground is. If we want to talk about reference, we can make the lowest position the child makes it to the reference level. I would encourage you to do so. If you don't, if you make the reference level something else, you're just adding the same thing to both amounts of energy. Like say you make the reference level way down here. Well, you're going to add a little bit of gravity for this height and a little bit of gravity in addition to that height. You're adding the same amount to both amounts of gravity. So I'd encourage you to use whatever the lowest position is as your reference level. If you do so, that suggests that the gravitational potential energy here is going to be 0 because we're at the reference level. We have no H in the MGH. Does that make sense? Now, if you start the person from rest, their initial kinetic energy is probably 0. They're not moving. But they should be clearly moving when they make it down to the bottom. In fact, if you want to know how fast the child is going at the bottom, this is probably the way to do so. Now here's our statement of conservation of energy. It says that the final potential energy minus the initial potential energy plus the final kinetic energy minus the initial kinetic energy has to equal 0. Now, you guys should look closely at this. I'm going to rearrange this just a little bit. I'm going to move the initials to one side and leave the finals on one side. And what it says is that if you add up all the energy you have at the start of the problem, you should be able to set it equal to all the energies you have at the end of your problem. Now, if there's work done on your system, it would show up here too. But right now, if you just add up the energies that you have here, it has to equal the energies that were here because there was no change in the total amount of energy. So if I tell you that you pulled the child back 40 degrees and that the length of the rope was 3 meters and you had a 15 kilogram child, we should be able to figure out how fast the child's going when it makes it to the bottom. Try it. I'll help you work it through. I'm going to go ahead and recognize that the initial kinetic energy was 0 because we're releasing the child from rest. And the final potential energy is going to be 0 because the child's going to be at the baseline. That means 1/2 mv final squared is the energy the child will have at the bottom. And mgh will be the energy the child has at the start. But we don't have h, do we? Do we have a way of getting h? Please say yes, because you were there for the whole first part of class. Good, good. It wasn't that long ago. It was quite literally 12 minutes. See what we're getting at here? Not particularly tough, is it? One thing that's important here, though, is do you see that the mass cancels out in this circumstance? So I didn't really need to give you the 15 kilograms for the child's mass. So don't be alarmed if you're doing a problem and they don't automatically give you mass. You're going to see the mass cancel out quite a bit. Because again, gravitational mass, inertial mass are the same thing. Now, plugging in your numbers and doing all the work there, that's fine. You know you're going to get an answer. And I don't want to spend too much time on it. But I do want to state at least one thing that's important here. If we take a look at the answer, which is going to be the square root of 2gl times 1 minus cosine theta. I just solved for v. I still haven't put any numbers in there. Please understand something important here. We don't know what direction the kid's going. In any conservation of energy problem, there's no direction. You have to get direction from context clues in your problem because energy can't tell you the direction of your answer. Remember, you're taking the square root. It can be any direction. So there's no vector information given here. Now, we know from the problem where the kid's going to be going. We know they're going to be on the swing and they're going to have a velocity in this direction. It's not a surprise, but again, you can only get direction from context clues in your problem. Now, I'd love to stop here, and I know you're plugging it into your calculator because the number part means something to you, but you understand that most likely the number part won't have any meaning, that they're not even going to give you numbers in the problem. Can I show you something else real quick before we run out of time? We don't do these problems in a vacuum. And what I mean by that is this is a great way of figuring out how fast the kid's going. We couldn't do this problem a week ago because we couldn't use forces to do so. There's no way of finding out the acceleration and figuring out how fast the kid's going from a motion equation because the acceleration was always changing in this circumstance. However, you now can figure out the velocity. And because of that, that suggests you can do other things as well. Like at this moment, the kid's moving this direction. Well, that is a tangential velocity. There are two forces acting on the child. There's tension upwards and there's weight downwards. This is a centripetal motion problem in that the net force at the bottom of the swing is MAC, which should tell you things like how much tension will be in the bottom of the swing and how does that tension change when you pull back the child further. I mean, we have an expression for velocity that will jump in right here. We have a lot of these kind of circle problems, and they're going to show up quite a bit. I mean, consider, can I switch to another page real quick? We will be going to Busch Gardens soon enough. So, do you see what I think is probably the obvious next kind of question? Based on what we just talked about? I've left it up at the front of the room for weeks now. Where do I have to start my car so it can successfully make it through the loop? I mean, consider what this problem is about if you really are thinking about it. I release the car's going to travel to different locations along the track, right? Aren't those reasonable places along the track where the car is going to go? Now, if I start the car high enough, I suppose the car is likely to make it to any part of the track that's at least that high. That's not necessarily true. I mean, I would like it to be true, but when the cart is here, I don't think there's any doubt in our minds that the cart will make it to the lowest point of the track here. But at this moment, the track is having to apply a fairly strong normal force upwards, right, in order to be able to make sure the car travels in a circular path. And then there'll be this point where the car is here. Well, if you'll recall, in order for the car to stay in contact with the track, there has to still be a normal force here, which means the car has to be going fast enough in this direction for the conditions of centripetal motion to still be in effect. This is where we're going tomorrow.